Thanks for the introduction, and thanks for Torvik and all the organizers for organizing this brilliant conference. So today my talk is about the Schur positivity of chromatic symmetric function of distributive lattices, and it's a joint work with Grace Li, Arthur Yang, and Zhongxue Zhang. Uh, so the main story is that we recently answered one of the question of Stanley that are all distributive lattices Schur positive? I mean the chromatic symmetry function, and we have a negative answer for this question, and we have further extended in the result to any non-chain times a long enough chain. So we'll start from the backgrounds. So the definition of chromatic symmetry function is by Stanley in 1995 and is well known. And I think so it's summing over all proper coloring of a graph. And for each proper coloring, we add a monomial that xi to the multiplicity of color I. So it's a generalization of the chromatic polynomial and have many nice property. One of the property that the combinatorics care about is the Schur positivity. And to study the Schur positivity, Stanley in 1998 defined a nice property for the graph, that a graph is called nice if and only if a partition lambda occurs as a stable partition, then all partitions that dominated by the partition lambda also occurs as a stable partition. So by the property of Schur functions, Stanley shows that Schur positive is stronger than nice property. No, yes. So the nice property cannot imply Schur positivity, but the non-nice can imply non-Schur positive. So sorry. So next we want to talk about the poset. So for a poset, it's not a graph, but we can consider the incomparability graph. It's called inc-p. We just add edge to those pairs that doesn't that are not comparable. So in our words, so stable partitions of the graph inc-p are exactly correspond to the chain partitions of the original poset p. So next is the distributive lattices. The distributive lattices are satisfying these two distributive laws. And many classical lattices are distributive, like chains and product of chains, including the Boolean lattices. So next comes the questions. The Greeks in 1988 proposed a conjecture or a question that is Boolean lattice Bn nice for every n? And since Schur positive is stronger than nice property, Stanley have a stronger version of this problem that is the chromatic symmetry function of inc B and Schur positive. It's a stronger problem. And after that, oh, so sorry. So Stanley have a wider problem on distributive lattices that is for any distributive lattice L is the chromatic function of the incomparative graph inc L also Schur positive. So it's not only for Boolean lattice, but also a question for all distributive lattices. So the question, after the question have come up in 1999, Long and Elzoby proved that any product of two chains m times n are nice. So it's nice, but not necessarily Schur positive. And in 2025, our group have proved that there are several family of non-nice and non-Schur positive distributive lattices give a negative answer of the Stanley's question. And later in 2025, Li Yang Zhang have defined the strongly nice property, which is also weaker than the Schur positivity, and they use it to prove several non-Schur positive. And very recently, our group again proved that if you have a non-chain poset and you multiply a long enough chain, it's eventually non-nice. That's non-Schur positive. So it's a more general non-Schur positive result. So we want to just go to the results. The first result is the family B3N it looks like this. First, we have a B3, which means a Boolean lattice is like a cube. And after that, we stick a very long how to say a ladder on the bottom of the cube. We call it B3n, and we show that this is of course a distributive lattice, and we show that if n is bigger than or equal to 6, this distributive lattice is not nice. And we just prove by definition that it has such a lambda, n plus 3, n plus 1, 2, a stable partition. And there is another mu, which is nn6, dominated by this lambda, but there is no chain partition of type mu because this chain have a so simple structure that we can show it in a few words. So now we have this uh, distributive lattice not nice and hence not sure positive, which is a negative answer to Stanley's question. But Stanley also mentioned that this may not be sure positive and it doesn't. At that time, they haven't found a counterexample, but it's not very likely that the distributive problem is true. So later we also consider that our example are not that nice. This is like how to say we stuck tuple set together, and then we look back to Long and Elzob's result that any product of two chains are nice. So we want to consider this kind of product of two chains, and we also find a infinite family of product of two chains that they are not sure positive. They are proved to be nice, but not sure positive. And what we use is some special rim hook tabloid method of aggluramel that it is actually a transition matrix from the monomial symmetric function basis to Schur function basis. And using that basis, one and one translate for the chromatic symmetric function, and we can get a formula for the Schur function coefficient for any chromatic symmetric function. And when taking a special role, like a staircase, we find that there are only 6 special rim hook tabloid. And using the formulas, there are some plus and minus sign, but adding them together, the coefficient of S row is a polynomial in n and k. And taking those values like k greater than or equal to 5 and n greater than or equal to another number, this polynomial is obviously negative. Thus, it is not sure positive because they have a negative coefficients. So we have proved this theorem. And for the product of two chain, Wang and Zhang have also followed do the further job. They prove that m times 2 and m times 3 are not sure positive for m greater than or equal to 8. So like you can see like when there is a product of two chains and the two numbers are too different, it tends to be not sure positive. Though they are nice, they are not sure positive. And we have another progress that on the yes, like last year, inspired by Elzoby and Long's result that any product of two chains are nice, we consider whether any product of any chains are nice. So we have this kind of conjecture. But very recently, we have found that this conjecture was false because we checked that 2 times 2 times c is already not nice for c equals 15, and it's not nice for all c greater than or equal to 15. So like a product of three chains is already not necessarily nice and not necessarily sure positive. So our counterexample, we can state it as a theorem because all the later theorems are based on the same idea, right? For taking c equals 15, so we can say this 2 times 2 times c looks like this prism, right? You have like a 2 times 2 times a very long c. And it obviously have a C chain composition, chain partition. Like you can see the two colored chains are the four Cs. So we have a CC chain partition. However, when we make the part from 4 to 5, we can find like a 4C over 5, which is a 12, 12, 12, 12, 12. And this partition is dominated by lambda, right? And dominated by lambda, but you see the prism only have four, like a four, how to say, four columns. Thus, it's not hard to prove that this 5/12 cannot be a stable partition for this, not stable partition, but cannot be a chain partition for this kind of poset. Thus, we have proved the non-niceness for the 2 to 15 case. And inspired by this idea, we further generalized it to any non-triple set. So let B be a non-triple set and let W be the cardinality. So if C is greater than the cardinality squared plus W, then B times C, like the B poset times a very long chain C, the product of the poset is not nice. So I think this is already a very nice and kind of how to say surprising result. And for this distributive lattice, I mean for this result, this B is not required to be a distributive lattice. It only need to be a poset, non-chain poset, because we have to have a we need to have like a width of 2. And if you look at the M times N times C, like the three-dimensional chain product case, when C is greater than or equal to this number, it's already not nice. And also, like if you look at the Boolean lattice 2 to the k, this bk times C is also not nice when C is big enough. So these are just straightforward consequences. So it surprised us because M times N is always nice, but when you look at the product of three chains, it is eventually not nice. And that's the last result. And here is a table that what we found, like something approved to be not sure positive, and something are conjecturally. And that's all for my talk. Thanks.